video, we are going to talk about the concept of the electric fields. So assuming we have two charges that are placed in this region of space, from Coulomb's law, the law says that there is going to be a force of attraction between these two charges. Nonetheless, if we take this charge away, the negative charge away, the concept of the electric field says that this positive charge, by virtue of its charge, modifies the region of space around it. So it possesses a force, but this force cannot be seen or detected except we put a test charge in the region of space around this positive charge before we can measure that electric force. But with reference to a single test charge, we will not call it electric force. It is called the electric field. It is not called electric force because a single test charge cannot exert a force on itself. Nonetheless, each charge, by virtue of the charges it carries, possesses a field that propagates radially outwards or radially inwards, equally in all directions in space. So the electric field is the means by which charges communicate. So if we have an electric field that is going in this direction and you put a positive charge in that field, the concept of the electric field says that the electric field of this positive charge will also go in the same direction as the original field in which it was put in. But if it was a negative charge, the direction of the field created by the negative charge will be contrary to the direction of the original field in which it was placed in. So the field on a positive charge acts radially outwards in all directions equally in space, and then the field on a negative charge acts radially inwards in all directions in space. Mathematically, the electric field is giving us the electric force divided by the test charge. Also, this is equal to 1 over 4 pi epsilon naught, then the charge divided by the square of the radius times the unit vector. So the electric force is a vector, and then the electric field is also a vector. The major difference between an electric field and electric force is that the electric force is in reference to two charges, but the electric field is the force on a single charge. Anytime the electric field is propagating in a certain region in space and it doesn't change, we call that electric field a uniform electric field. So let's take some examples and explore this concept. A point charge Q equals minus 8.0 nanocoulombs is located at the origin. Find the electric field vector at the point x equals 1.2 meters and then y equals minus 1.6 meters. So let's assume this is the point charge, but because it's minus 8 nanocoulombs, we know that it is a negative point charge. And then, so we want to measure the electric field at somewhere here, P. Now, from the question, the horizontal component is 1.2 meters. And then the vertical component is minus 1.6. So here's minus 1.6 meters. So in other words, we are moving this way. So in terms of vectors, we can join these two together. So you can see that this is right angle triangle, so we can use Pythagoras theorem. So let's put r here. So r is equal to the square root of 1.2 squared plus minus 1.6 squared. And if you do this, you are going to get 2.0 meters. So that means this portion is 2.0 meters. But then remember that from theory, we said the electric field is equal to 1 over 4 pi epsilon naught. Then the charge, which is this negative charge, divided by the square of the radius. So in this case, The distance is 2. So let's put it here and find the magnitude of the electric field. So the electric field, E, is equal to, now 1 over 4 pi epsilon naught is the same as 9 times 10 exponent 9. Then times the charge, which is minus 8 times 10 nanocoulombs is minus 9. Then divided by the square of the radius. The radius is 2.0 meters. So it is 2.0 all squared. So if you do this, the magnitude of the electric field is equal to minus 18 Newton per coulombs. But remember that we are looking for the electric field vector, so we need to find the vector. Remember that let me modify this formula. So the electric field vector is this constant times the unit vector. So let's find the unit vector. Remember that the unit vector is equal to x in the unit vector I, then plus y unit vector j divided by the square root of x squared plus y squared. So in that sense, the unit vector is equal to, now the x is 1.2, so 1.2 I, then the y is minus 1.6 j divided by the square, which is 1.2 squared, then plus minus 1.6 squared. So r hat is equal to 1.2 I minus 1.6 j divided by, if you do this, that's what we did initially, we got 2.0. So r hat is equal to 1.2 divided by 2.0 is equal to 0.6. So here 0.6 I, then 1.6 divided by 2.0 is 0.8, so minus 0.8 j. So what it means is that the electric field vector is equal to the magnitude of the electric field times the unit vector. Magnitude of the electric field, which is what we calculated here, times the unit vector. So the electric field is equal to minus 18 nanocoulombs, Newton per coulombs, then times 0.6 I minus 0.8 j. So this is equal to, now minus 18 times 0.6 is minus 10.8 I, then minus 18 times minus 0.8 is plus 14.4 j, then newtons per coulombs. So this implies that the electric field is equal to, into bracket, minus 10.8 I plus 14.4 j newtons per coulombs. A point charge plus 2 microcoulombs is at the origin, and a second minus 5 microcoulomb point charge is on the x-axis at x equals 0.8 meters. Find the electric field, into bracket, magnitude and direction at x equals 0.2 meters. So that means, since he's talking about magnitude and direction, he's talking about the electric field vector. So let's try and then sketch it. So we have a plus 2 microcoulomb at the origin, then minus 5 microcoulombs on the x-axis. So let's put the minus 5 microcoulombs here. The distance between the two of them is 0.8 meters. But we want to find the electric field at 0.2 meters. So from this origin, 0.2 meters is somewhere here. So let's label that as B. So here is 0.2 meters. If here is 0.2, the total is 0.8. So it means that here is 0.6 meters. So what we will do is that we will find the electric field due to the positive charge, the electric field due to the negative charge. Then we will sum them algebraically. Now, remember what we said. The electric field around a positive charge spreads out radially outward. So with reference to point B, the electric field here, let me label that as E plus, is going in this direction. Then the electric field of a negative charge points towards the negative charge. So with reference to this point B and this negative charge, the electric field here, it will go in this direction. Now, these two charges, which one has the greater electric field? Remember that their charges are the same. So the one with the greater electric field will be the one is closest to the point at which we are measuring the electric field. And in this case is the positive charge, and therefore the magnitude of the electric field with reference to the positive charge would definitely be greater than the magnitude of the electric field with reference to the negative charge. But we know that from theory, the electric field is giving us 1 over 4 pi epsilon naught, then times the charge divided by the square of the radius times the electric field vector. Let's find the magnitude of the electric field with reference to the positive charge. So E plus is equal to, now all of this is 9 times 10 exponent 9, then times the charge, which is 2 microcoulombs, so 2 times 10 exponent minus 6, then divided by the square of the distance, which is 0.2 squared. And if you compute that, you are going to get 4.5 times 10 exponent 5 newtons per coulombs. But remember that this is going in the positive x direction, and therefore in terms of the electric field vector, E plus is equal to 4.5 times 10 exponent 5 I Newton per coulombs. Now let's come to this negative charge. So it's the same thing. E minus is equal to 9 times 10 exponent 9. But with reference to the negative charge, the charge it carries is minus 5 microcoulombs. So minus 5 times 10 exponent minus 6 divided by the square of the radius, which in this case is 0.6 squared. So E minus is equal to, if you compute this, is minus 1.25 times 10 exponent 5 newtons per coulombs. So now, in terms of the electric field vector, remember that this is also going towards the positive x direction. So this is minus 1.25 times 10 exponent 5 I Newton per coulombs. So the total electric field at B, E of B, is equal to the electric field with reference to the positive charge plus the electric field with reference to the negative charge. So EB is equal to, with the positive charge it was 4.5 times 10 exponent 5 I. Then with the negative charge is minus 1.25 times 10 exponent 5 I. All of this, then the unit is newtons per coulombs. So EB is equal to, now if you compute this, 4.5 minus 1.25 is equal to 3.25 times 10 exponent 5 I newtons per coulombs. So the electric field is 3.25 times 10 exponent 5 newtons per coulomb in the positive x direction. Two protons are 5 nanometers apart on the x-axis. A point B is 3 nanometers to the right of the proton on the left hand side. The electric field at point B is, so let's draw the two protons. So let's say this is proton 1, and then this is the second proton on the x-axis. They are 5 nanometers apart. Now the point B is 3 nanometers to the right of the proton on the left. So this is the proton on the left. Point B is 3 nanometers to the right. So this is to the right, and this is 3 nanometers. So if it is 5 nanometers, then the remainder is what, 2 nanometers. So we are supposed to find the electric field at B. But now, let's label this as proton 1 and then proton 2. With reference to the proton 1, remember that we said for a positive charge, the electric field goes radially outwards. So with reference to point B, the electric field that's here due to proton 1 will be going towards the positive X direction. And then with reference to proton 2, since it is also a proton, the electric field at B will be going towards the negative X direction, because the electric field always goes radially outwards. So now the total electric field EB will be equal to which of these two protons will have the greatest electric field with reference to the distance. So considering the distance alone, you see that the one that is closest to B will have the greatest electric field, and that will be proton 2. So the total electric field is going to be the second proton, which is E2, then minus the first proton, which is E1. So let's calculate E2. E2 is equal to, remember the formula for electric field mathematically is 1 over 4 pi epsilon naught, the charge over the square of the radius times the electric field vector. So in this case, it's 9 times 10 exponent 9, then times the charge is a proton. The charge of a proton is 1.6 times 10 exponent minus 19 divided by the square of the radius between them. So at B, this proton 2 is 2 nanometers, so it's 2 times 10 exponent minus 9 squared. So E2 is equal to, however, E2 is going in the negative X direction. So we need to put a negative value here. So here is negative I. So E2 is equal to, if you compute this, you are going to get minus 3.6 times 10 exponent 8 Newton per coulombs. Sorry, there's an I here, so I. So let me rewrite this. So E2 is equal to minus 3.6 times 10 exponent 8 I newtons per coulombs. So E1 is equal to 1 over, so 9 times 10, then times the charge of the proton is 1.6 times 10 exponent minus 19 divided by the square of the radius. So the radius here is 3 nanometers, 3 times 10 exponent minus 9. But then it's going in the positive X direction, so we need to put I here. So this E1 is equal to this 1.6 times 10 exponent 8 Newton per coulombs. The electric field EB, which is equal to E2 plus E1, this is equal to minus 3.6 times 10 exponent 8 I. Then, sorry, let's correct this mistake. So E2, remember that we are summing them algebraically. So here is supposed to be plus. So this is in terms of their magnitudes. But in terms of their vectors, we are just adding the electric fields about B. So since this is vectors, then here is minus 3.6 times 10 exponent 8 I, then plus 1.6 times 10 exponent 8 I newtons per coulombs. So the electric field E of B is equal to minus 2 times 10 exponent 8 I newtons per coulombs. Please, let's take notice of this correction. Now, this EB equals E2 minus E1 is in terms of their magnitudes. But if it was in terms of their vectors, then EB is equal to the vector sum of E2 and then E1. So these are two different equations. So it's either you calculate it in terms of their magnitudes and do this subtraction, or you calculate it directly in terms of their vectors and just add all the electric field about the point at which you are making the calculation. Two identical charges with a magnitude of +1 microcoulombs are separated by a distance of 1 meter as shown below. At what point will the net electric field be 0? If the charge on Q2 is doubled to +2 microcoulombs, where along the x-axis relative to the first charge will the electric field be 0? So let's draw the two identical charges. So we have one charge here, and then this is the second charge. So each of them is +1 microcoulombs. So this is +1 microcoulombs. And then the distance between them is 1 meters. So the distance from here to here is 1 meter. Now, at what point will the electric field be 0? So let's assume that the electric field will be 0 at this point called B. So let's say if the electric field, the distance between this charge and B is x, the total distance is 1. So the distance between B and this charge will be 1 minus x. So now, with reference to this point, what will be the nature of the electric field? You see that the nature of the electric field here, with reference to this charge, will be going towards the positive x direction. And with reference to this charge, it will be going this direction. So if we sum the electric fields about B, then we will get the point at which this electric field is 0. EB must be equal to 0. But we know that the electric field about B is equal to the electric field. Let's say this charge is charge 1 and charge 2. So it's the electric field with reference to charge 1. Then plus the electric field with reference to charge 2. So now we know that from theory, electric field is equal to 1 over 4 pi epsilon naught, and the charge divided by the square of the radius. The electric field in this case, E, so E1 is equal to K 1 over 4 pi epsilon naught. I want to represent all of that by K. Then the charge is +1 microcoulomb. So times 1 divided by, now the distance between 1 and then B is x, so x squared. So this is, then we are working, this one is going in the positive x direction, so I. So E1 is equal to K over x squared I. And then now let's calculate E2. E2 is also going to be K times 1 microcoulomb, so times 1 divided by the square of the distance between E2 and B, sorry, the second charge and B, and that's 1 minus x squared. However, E2 is going the negative x direction, so here becomes times minus I. So E2, sorry, is a vector, so E2 is equal to minus K over 1 minus x all squared. So EB is equal to K I over x squared, then minus, remember, plus E2 here is minus K divided by 2 bracket 1 minus x all squared. But we said the electric field must be 0 at some point. So here's I, actually. Sorry, I forgot to bring the unit vector. So we can factorize some things. So let's factorize Ki out. So if we factorize Ki, we are left with 1 over x squared and minus 1 over 1 minus x all squared. And all of this is equal to 0. So you see that this can only be 0 if 1 over x squared minus 1 over into bracket 1 minus x all squared is equal to 0. So let's multiply through by x squared times into bracket 1 minus x squared. So if we do that, so here's x squared times 1 minus x all squared, then times 1 over x squared, minus x squared times 1 minus x all squared, then times 1 divided by into bracket 1 minus x all squared. So you see that this x squared and this one will cancel. This is equal to 0 actually. And this one and this one will cancel. So we now have 1 minus x all squared, then minus x squared equals 0. If you expand this, it is 1, then minus 2x, then plus x squared minus x squared equals 0. So we have plus x minus x can cancel out. So we have 1 minus 2x is equal to 0. So this implies that x is equal to 1 over 2. So the point at which the electric field is 0 is x equals 1 over 2. The second part of the question says if the charge on Q2 is double 2 plus 2 microcoulombs, where along the x-axis relative to the first charge will the electric field be 0? So everything remains the same, just that the plus 1 microcoulombs is now plus 2. So let's recalculate the electric field of the second charge. So E2 becomes K, then times the charge. The charge now becomes 2. Then 2 microcoulombs divided by into bracket 1 minus x all squared. Then times the unit vector, but it's going in the negative x direction. So that's negative I. So E2 is equal to minus 2k divided by 1 minus x all squared. So we can now sum. So EB is equal to the first charge, the electric field of the first charge, which is ki over x squared, then plus the electric field of the first charge, second charge, which is minus 2, here is I, minus 2ki over 2 bracket 1 minus x all squared. And this must be equal to 0. So let's factorize ki out. If you factorize ki, you're left with 1 over x squared, then minus 2 over 1 minus x all squared. And this is equal to 0. But this can only be 0 except if and only if the thing that is in the bracket is 0. So it means that 1 divided by x squared minus 2 divided by 1 minus x all squared should be equal to 0. So let's multiply through. Multiplying through, we get x squared and times 1 minus x all squared times 1 over x squared. Then minus x squared times 1 minus x all squared times 2 divided by 1 minus x all squared. This is equal to 0. So this one and this will cancel. This and this will cancel. So we are left 1 minus x, all squared, then minus 2x squared equals 0. So if you expand this is 1 minus 2x, then minus plus x squared minus 2x squared equals 0. So let's rearrange. We now have 1 minus 2x. Then this one, x squared minus 2x squared is minus x squared equals 0. So in this case, to be able to find x, we need to use the quadratic equation. You can see that if we rearrange these equations of the form x squared, then plus 2x minus 1 is equal to 0. So you see that this is of the form ax squared plus bx plus c equals 0. So let's use the quadratic formula. So x is equal to minus b plus or minus square root of b squared minus 4ac divided by 2a. So x is equal to x is equal to minus b. So minus b in this case is minus 2 plus or minus square root of b squared, which is 2 squared, then minus 4 times a is 1, then times c is minus 1, divided by 2 times a, 1. So if you do all of this, you find out that x is equal to 0.414 meters. An electron initially at rest is placed in an electric field of 2 times 10 exponent 4 Newton per coulombs, directed to the west. The distance between the plates is 1 centimeters. A. What is the acceleration of the electron due to the electric field? And B. What will be the speed of the electron after it leaves the hole? The mass of an electron is 9.11 times 10 exponent minus 31 kilograms. So we know that from theory, the electric field is equal to the force over the charge. That is, the magnitude of the electric field is equal to the force over the charge. So making force the subject, the force is equal to the electric field and times the charge. So let's calculate the force. We're given the electric field at 2 times 10 exponent 4. Then charge of an electron is 1.6 times 10 exponent minus 19. If you do this, this is equal to 32 times 10 exponent minus 16 newtons. Now, we know that from Newton's second law, the net force is equal to mass times acceleration. So, we know the force and we're given the mass. So, let's make acceleration a subject. So, acceleration is equal to the force divided by the mass. And the force is 32 times 10 exponent minus 16 newtons, divided by the mass, which is 9.11 times 10 exponent minus 31 kilograms. And if you compute this, you are going to get 3.51 times 10 exponent 15 meters per second. Now, the second part is, what will be the speed after the electron leaves the hole? We know that from the laws of motion, v squared is equal to v naught squared plus 2as. But the v naught is the initial velocity. The question says that the electron is initially at rest. It means that v naught is equal to 0. So this implies that v squared is equal to 2as. And therefore v, in this case, is equal to square root of 2as. A is the acceleration. So v is equal to square root of 2 times the acceleration we found is 3.51 times 10 exponent 15, and times the distance. We're given the distance at 1 centimeter, which is the same as 0.01 meters. So v, if you calculate this, we are going to get 8.38 times 10 exponent 6 meters per second.